All right, today we are diving headfirst into the absolute bleeding edge of communication tech. We're talking about a place where the normal rules of electronics start to get, well, a little weird, and the potential for speed is just mind-blowing. This is all about conquering what's called the terahertz frontier, and it just might be the great leap that defines our 6G future.
So what is this terahertz frontier anyway? I know, it sounds like something straight out of science fiction, and honestly, it kind of is. The best way to think about it is like a massive, undiscovered continent of wireless data, just sitting there, waiting for us to figure out how to use it.
And look, this isn't just some abstract thing for physicists to argue about. This frontier, it's the key. It's what's going to unlock 6G and everything that comes with it. I mean, we're talking about speeds that make 5G look like dial-up. Think about virtual reality that feels completely real, with zero lag. Or a world where trillions of devices are all talking to each other instantly. That's the promise here.
But of course, there's a catch. There's always a catch, right? For decades, this whole slice of the spectrum was known as the terahertz gap. And for a really simple reason, we just didn't have the right tools. Our electronics couldn't go that high in frequency, and our lasers couldn't really go that low. It was this technological no man's land, stuck right in the middle.
So, to finally bridge that gap, to build a highway across that no man's land, scientists needed a very specific kind of tool. You could think of it as a ruler, but not for measuring inches or centimeters. This is a ruler for frequencies, a ruler for light.
And that tool has a name. It's called a frequency comb. Now, just picture this. Imagine a laser that doesn't just shine one single pure color. Instead, it shines hundreds, maybe even thousands of perfectly sharp, perfectly spaced frequencies all at the same time. If you were to plot them on a graph, they'd look exactly like the teeth of a comb. And it's that precise, ruler-like structure that makes it so incredibly powerful for communication. Yeah, you can really see the idea here. Each one of those sharp lines is like its own pristine data channel, a separate lane on our superhighway, and they're all coming from a single device. The crazy part is, this isn't just about getting faster downloads on your phone. This kind of technology could revolutionize everything, from medical scanners to being able to detect chemicals from a distance. Okay, so for the longest time, in this quest to build the perfect terahertz comb, there has been one clear, reigning champion.
Let me introduce you to the Quantum Cascade Laser, or QCL for short. This thing is a true heavyweight. We're talking a 30-year legacy of just constant breakthroughs. It first showed up on the scene back in 1994, and since then, it's just gotten more and more powerful, becoming the absolute go-to technology for generating serious laser power in this frequency range.
So how does it work? Well, on the left, you can see this incredible internal structure they call a quantum staircase. It's this stack of super thin, specially engineered layers. And as a single electron tumbles down this staircase, it emits a photon, a particle of light, at every single step. It's an amazing design. And on the right, you can see the results of that design. Just a relentless, steady march towards more and more power over the years. No wonder it's been the champ for so long. But, you know, every champion has an Achilles heel. And for the QCL, that weakness is heat. To get these terahertz waves out of it directly, you usually have to cool the thing way, way down. We're talking cryogenic temperatures with liquid nitrogen. And that means the whole system ends up being big, complicated, and pretty darn expensive. Not exactly something you can just pop into your next smartphone, right?
And that limitation, that's what created an opening. It left the door ajar for a new challenger to step into the ring, a completely different kind of technology. And here it is. Say hello to the Resonant Tunneling Diode, or RTD. Now, just forget everything I said about big coolers and complex lasers. The RTD is a tiny little electronic chip. It does all its magic with just electricity, and this is the real game changer, it works perfectly fine at room temperature.
So what's its secret weapon? Well, it's a really bizarre quantum mechanical trick. It's called negative differential conductance. Now, in pretty much any electronic part you've ever heard of, when you increase the voltage, the current goes up. Simple. But look at this graph. For the RTD, there's this weird little region where you increase the voltage and the current actually goes down. It's completely backward. And it's that strange counterintuitive behavior that lets it oscillate at these incredibly high terahertz frequencies. Okay, so how do you go from that single frequency to a whole comb? It's actually a pretty clever three-step recipe. First, you have the RTD just doing its thing, producing one single, clean terahertz note. Then, you inject a weak little radio signal, which is like adding a few extra harmony notes on the side.
But step 3 is where the real magic happens. You hit it with a strong radio signal, and that forces all those different notes to lock together, perfectly in sync. It's a process called active mode locking, and the result is that beautiful, broad frequency comb.
So the theory is absolutely brilliant. But the real question is, can this tiny little quantum device actually perform in a real-world, high-speed data test? Well, here's the actual hardware. I mean, look at that thing. The RTD itself is smaller than a grain of rice, and it's packaged inside that little gold component, which is a waveguide that helps direct the signal. This isn't a lab experiment the size of a table. This is real, compact, chip-scale tech you can hold in your hand.
And just look at the signal it kicks out. Wow, that is a beautiful, stable, and incredibly wide frequency comb. Every single one of those sharp spikes is another potential channel for data, all coming from that one little chip. The quality here is it's spectacular.
So, the researchers used this exact device as a transmitter to send actual data. The speed they hit? An absolutely incredible 12 gigabits per second. And remember, that's just on one of those channels. With dozens of channels available, well, you can do the math. The potential speed is just astronomical.
And here's the proof in the pudding. These charts are called constellation diagrams. Think of them as a target. When you send data, you want all the dots to land in tight, clean clusters right in the center of those targets. The messier they are, the more errors you have. And as you can plainly see, even at 12 gigabits per second, those clusters are tight. The data got through clean. It's a massive success.
So, what we have here is a classic story, right? The reigning champion and a powerful new challenger. Which brings us to the future, a future that is still very much unwritten.
Now, this isn't necessarily a story about one technology knocking the other one out. It's more like they're taking two different paths to conquer the same frontier. You've got the QCLs, the champion, focusing on raw brute force power, perfect for things like long-range sensing or satellite communications. And then you have the RTDs, the challenger, focusing on being small, efficient, and easy to integrate into tiny chips for our phones and gadgets.
And that leaves us with one big, fascinating question. As we start to build this 6G world, what's going to be running under the hood? Will it be the raw power of microscopic lasers, or the compact elegance of these tiny quantum turnstiles? You know, the most likely answer is both. Each will find its place. But the competition, the race between these two amazing technologies, that is what's going to define the next decade of communication.